from lattice QC. So what we do, so the specific wise precision frontier of particle physics, because you know that there is a standard model which is really successful in explaining a lot of things, but there are clear hints that there are physics beyond that, and throughout like US, Europe, Asia, there are many experiments, many efforts going on to find out what is the new physics. So you know there is a cosmic frontier of particle physics where cosmos is the universe. Then there are like cosmic ray gamma ray detections, dark matter search, dark energy search experiments are going on. Then there is the energy frontier of particle physics, where basically the aim is to achieve the highest possible energy of the smashing particles to cover the threshold of some heavy new particle, and the search is going on. And then there is a complementary third frontier of particle physics, which is the intensity frontier or precision frontier. And here, you don't really need that high energy. Comparatively, at low energy, one can do this kind of experiments of rare processes where the intensity of the particle beams are really huge, and the detectors are very sensitive. So it is high precision experiment, and then if you know the expected result from theory, from the discrepancy, you know what sort of, like you can probe the large scale new physics effects, and those come from the loop corrections at the tree level. So from at low energy we get like a small window to probe the high energy effects, and this has been very successful. So many experiments are going on there, and in this frontier, the flavor physics program is a very fertile ground to test the beyond standard model physics effects. So in flavor physics, and the flavor changing weak interactions can change one quark flavor to another quark flavor. So if meson decays and different kinds of weak decays, leptonic or semi-leptonic, if we can probe them from different processes independently, then we can search for new physics effects. Now this flavor changing weak interactions can be parameterized in terms of a matrix which is known as Kabilo-Kobayashi-Maskawa matrix or CKM matrix, and the matrix is unitary in the theory. So here these are the different elements, and this UD, they represent like from which flavor to which flavor it changes. And if you see the unitary to relationship, then, sorry, somehow this is scaled badly, so it's not coming like. Do something about it. Thank you very much. So basically, if you see the unitarity relationships, so the first row unitarity, this is very precisely measured and verified. The first column unitarity also very precisely measured and validified. But if you see the second row or second column unitarity, these are not as precisely determined as the first row and first column, and the main reason being that the central CK matrix element, the determination of this matrix elements from different leptonic and semi-leptonic processes, and there are huge uncertainty in this BCS matrix element. BCS element, and if you see these diagrams, then this blue portion, which is the 64%, this is coming from the lattice QCD determination of these processes. So that's why we are more interested to determine these processes from D to K meson semi-leptonic decay, and just improve the lattice precision or lattice overall lattice calculation of this element. Now, how do we do that? We have to actually have both experimental results for this decay, the partial rate decay rates, which is this d omega dq square, And for each q square, which is the momentum transfer square from d to k meson in the decay process, for each q square being, we have to have this vector form factor 8 plus, which we calculate from the lattice QCD. And in this talk, I am going to talk all about how we calculate this and what results we get. And then if we take the ratio of this experimental result to this lattice results, we get VCS mod VCS square. So that's our goal. However, here we are not just trying to get, so a lot of collaborations get at q square equal to 0, because that's what we actually need to get VCS. But our goal is to compare the full shape for all possible physical q square, the full shape of the lattice F plus this to the experimental, and then we want to calculate mod VCS square from each q square being. So the calculation needs a lot more computational power and some techniques to do that. Now, how do we do that? So this is the matrix element between D naught and K minus meson, and this is the weak current interacting with this, and this is the matrix element we are trying to calculate. Now, this can be divided into two parts, which one is purely electronic part, which can be derived by hand, and then there is the hadronic part. Now, in hadronic part, the first one, gamma mu, is the DiRAC gamma matrices, and this is the vector part, and then there is gamma mu, gamma phi part. Now, since this is a pseudoscalar, so pseudoscalar decay, so D meson and K mesons are both pseudoscalar mesons with spin 0. That's why only the vector part of the current will contribute. So we don't have this gamma mu, gamma phi part in our actual calculation. So from lattice, what we are trying to do to calculate this matrix element perfectly renormalized by this multiplied by this renormalization constant, which can be calculated perturbatively, but in our calculation we use the scalar current matrix element to calculate this completely non-perturbatively. And this matrix element can be written in terms of two form factors. One is the vector form factor 8 plus, and one is the scalar form factor 8 naught. And then this momentum, this is the momentum of D meson, this is the momentum of K meson, mass of D meson, mass of K meson, and these are all kinematic factors. So we can extract those, so momentum we know, we just put them by hand, and these masses we extract from our calculation, lattice calculation. So now we also use the scalar current, which multiplied by the difference of the masses, bare masses of charm and strain. This multiplication, this factor is completely renormalized, perfectly renormalized, so we don't need any z factor for this. And from q square max, which is given by this, the maximum possible momentum transfer at 0 equal of k meson, basically we can calculate this ZV renormalization factor by putting F naught value and then taking out this kinematic factor, because we know this matrix element of the vector current, we know F naught and we know this thing, so we can calculate ZV and then use that ZV from q square equal to 0 calculation for all other q square. So this is our how we do it. Now here we use the local temporal vector current, and this current is not conserved in our lattice simulation because of the discretized action we use. That's why we need this ZV factor. In this calculation, we need to calculate 2-point correlators. So a correlator in lattice QCD is same as the correlator definition in quantum field theory. Like a meson is created at one point, so this is a lattice point, and then travel to another lattice point, and then destroy the probability of this process. That's the basically the correlator gives that. So this is the D meson correlator, this is the K meson correlator, and then we have to calculate the 3-point correlator, where we start the calculation at t equal to 0 at K meson. Then we invert the DiRAC action to get the propagator of this light wave. So we are using the strange quark here, and the light quark is the spectator quark. And then at this point, at capital T time, basically, we create a sequential propagator. So we invert the to get the charm propagator here, And again, from here at t equal to 0, we create the strange propagator and tie all of them together. So this technique is known as sequential technique. And here the current is interacting, basically J, which is both vector and scalar current represented by J. So we need the matrix element for both of the currents. Now the usual lattice calculation, other people like in morning they have said, so I'm not going into that. So we need the 2-point and 3-point correlators, and we can express them in terms of summation of different exponentials, where in the exponentials, this is the 2-point correlator, this E ends basically denote the energies of the meson. So if it's for D 2-point correlators, is the energies of radial excitations of different for D meson. So E0 is the mass of the meson, and AN is amplitude, and this amplitude is related to the decay constant of the meson is perfectly normalized. Then for 3-point function also, we have this kind of amplitude, and actually the amplitude we need for equating with the matrix element is this B for the ground state. So this is what we need to extract, and since there are so many parameters and exponentials, so we do a multi-exponential Bayesian fitting to extract these numbers. These are our lattice ingredients that we are using. So we are using mill configurations with up, down, strain and charm quarks in the C. So vacuum polarization effects are coming from all of these quarks. We don't differentiate between U and D, so mass of U same as mass of D in our simulation. We use 6 ensembles with heavier and physical point quark masses, and then 3 different lattice spacing at both masses, starting from 0.09 Fermi, which we call fine, then coarse, then very coarse at 0.15 Fermi. Our masses, the valence quark masses, strain and charm are very finely tuned, so the mixing effects are almost 0, and we use very high statistics like 1000 configurations at each ensemble with between 4 to 16 time sources. So this is our setup, and then we use twisted boundary condition to apply any momentum necessary, because we want to cover the whole range of momentum, and also we use random wall sources to increase the statistics. Now with all these ingredients and our formalism, we extract the results. So one check of our discretization effect is that plotting this relativistic dispersion relation. So calculate the velocity of light from our extracted kaon energy and mass of kaon, and P, the momentum of kaon we know because we put it by the twist, momentum twist by hand. And then 1 should be, in the continuum C square should be 1, and we see how it is deviated in our calculation, and we see the maximum deviation on the coarsest of lattices is not more than 2%. So which is a good check that our data is fine. Then we progress through extracting the matrix element and F plus, but the question is that we have discretized value of 4 or 5 Q square for F plus and F naught, the form factors. How do we get the shape? So to get the shape, to extrapolate, we actually convert to Z space, which is known as common Z expansion. And what we do is that we define the variable Z in terms of T plus and T minus, where T plus minus is basically mass of G plus minus mass of K whole square. And this is the form we have. For the very simple fit, we take T0 equal to 0, which basically allows us to overlap Q square equal to 0 to Z equal to 0. And this Z expansion also allows us to map this semilaptonic region in Q square space to this Z within unit circle, to map within unit circle such that we can expand the function in Z space as a polynomial. And that's what we do. So basically the Q square dependence is in P phi, this function, and the simplest form is the dipole form. We take 1 minus Q square over mx square, where mx is the mass of the relevant pole mass. So for scalar form factor it is m ds naught star, and for the vector it is m ds star. So for the expansion coefficients b ends, we have the chiral continuum extrapolation, the form within this Q square expansion terms, and this is how the coefficients look like. So we have that a square, a4 terms for the continuum extrapolation. So this is the discretization effects we have. And since we are using highly improved staggered quark actions, we don't have any order A effect in this. So we start from a square. And then there are chiral logs to take care of this chiral extrapolation. Although we are using physical point lattices, but there are also heavier masses in this, so we need this chiral logs to take care of that. And after that, you see our results. So we have q square at this q square or z point discrete results, and this is the extrapolation curves for f naught and f plus. And the from the curve, it is very clear that the forms are actually very simple. So and then we convert it back to q square space to get the q square shape of the form factor, and we extract the value at q square 0, which is actually needed for calculation, but we are still going to calculate at each q square b. Now we compare the shapes of the form factor with different experimental data. So from Bayes, Bauer and Cleo, and this is the blue points are HPQCD results, and we at the 48% confidence limit, we compare the confidence ellipses. This is coefficient B2 over B0 versus B1 over B0, and we agree well with the experimental results. But to get the shape, we have to use the exact experimental form of T0 that experimentalist used, which is complicated, but this is how they have done, so we compared with this. Now finally, we calculate the VCA square from the ratio of the experimental decay rate to the lattice calculation for each q square bin, and we see the most precise results come from the total decay rate of Bell and base 3, and also for each q square bin the result is pretty consistent. For the lower q square, the experimental result is very precise. For higher q square, the lattice result is very precise. So basically, for average, we need to take some value, like fitted value, in some region between 0.2 to 1.2 GeV square. And I have not yet given a number here because we are still fine-tuning for our paper. So our result is the first results with like full physical range of q square with physical point lattices and 2 plus 1 plus 1 quark flavors. There are many competitive results as well from ETLC. They have done it with everything like 2 plus 1 plus 1 full range of q square, but not at physical point. For milk, they are doing physical point 2 plus 1 quark flavors, but not full range of q square. And JLQCD, they are also not doing physical point, and they are doing just 2 plus 1 flavors. So our result is and I just take few seconds. So we thank DiRAC 2 and DiRAC 2.5 because most of our data came from there, and we used few 100,000 core hours at Darwin and also about 100 terabytes of stored propagators, which really lowered our cost of computation because we could use that storage space. And this DiRAC resources helped us to get the results at many different lattice points and physical point lattices with a better control over the systematics. And the future is to calculate many more form factors like Jad has discussed in the morning. Thank you very much.